because each of my units has kind of got some calculator stuff and it's got some pretty stuff. So we kind of descriptive chemistry. We already talked about descriptive chemistry, about like what the atom is and where the electrons are and kind of why they're important to an atom. We talked about the periodic table. So all of that stuff will be on your Unit 2 exam. Now we need to talk a little more about numbers, okay? So I'm going to introduce you to the concept of a mole. So when we talked about standard units of measure, like the meter, the second, you know, those are for length and time. Mass is kilograms, actually. We talked about amount in physical science is the mole, okay? So a mole, I'm going to try to kind of help this sink in tomorrow's lab, or it's not tomorrow. When we meet again on Thursday, Thursday's lab will kind of reinforce this. But a mole is 6.022 times 10 to the 23rd. So make sure we're all on the same page about that. So the fact that we have 10 raised to the 23rd power means that if we want to unpack that, we have to move that decimal place over 23 places. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, so you get the idea. We put zeros in there, and that's how many a mole is. So why do you think, well, I'll answer it. Atoms are really small, so in order to have something you can actually sink your teeth into, that's how I think of it. We need to not invent, but we need to have a concept of something of a big number. All right. So that number, a mole, is called Avogadro's number, and this is where it sounds like something you eat. We ran into Avogadro's number the other day, and actually it can be helpful from working homework problems. We said 1 gram is approximately equal to 6.022 times 10 to the 23rd what? Do you know? What units are these? So we have a unit of a mass. Grams is a mass. AMUs, very good. Yep. Oh, can I? Okay. So, yeah. And this is one of my favorite. I just love this. You know, scientists are so funny. So instead of MOLE, you get to drop the E. It's the abbreviation MOL. All right, it's the little things. So we talk about kind of quantities like a mole when we talk about a dozen. So we talk about a quantity of 12 if we have a dozen, okay? So if you have a dozen eggs, you have 12 eggs. Now, if you have if you have a mole of eggs, you have 6.022 times 10 to the 23rd eggs, and that's a lot. That's problematic. That's a lot of eggs, okay? So you saw the equivalency statement. You've seen kind of a couple of equals statements. 1 mole is equal to 6.022 times 10 to the 23rd. We're going to go probably atoms. 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. Those equivalency statements are going to be great to work in conversion problems. But instead of going to atoms, I kind of want to scale it up to something macro. So I've got some rice. I've got some things to kind of think about with regard to how much a mole is. So you might think, how many rice grains do you know how you count the jelly beans? Just how many rice grains do you think that might be? 1 million? I wrote it down. The rice grains here is 2 times 10 to the 4th. 2 times 10 to the 4th. So 2, 1, 2, 3, 4. What, 20,000? So close. So close. Right. 20,000 rice grains. And in terms of a mole, and I did that, we're going to be doing these conversions. In terms of a mole, it's only a fraction of a mole. 3.3 times 10 to the negative 20th mole. Okay? So it's just a fraction of a mole. So rice. So if we had a mole of rice grains, remember I said if you had a mole of eggs, you would be in trouble? If you had a mole of rice grains, you would be in trouble too. No matter how small they are. Atoms are much smaller. So they actually would cover the land area, which the Earth is like, what, 3/4, is it 3/4.
75% water, I think.
Okay, I thought it was, 75% water, only 1/4 of the earth was covered with land. Like, all the land would be 75 meters deep. All right, so the thing though is a mole of rice grains have, as much as a lot of people eat rice, a lot of cultures, it's their staple, not that many rice grains have been grown since people have been eating it. That's so cool. Okay, here's another one. If you had that mole of rice grains, you could confine it to a cube with the same dimensions on all sides, and that cube would have to be 120 miles by 120 miles by 120 miles. So that's a lot of rice, just for a mole. Okay. Marshmallows, I always think of like the Ghostbusters, right? Marshmallows would be a bad thing too. Cover United States up to a depth of 600 miles. And people can do these calculations. We have our snow events here in the Midwest. So if you were to have a mole of snowflakes, you'd be in trouble. Cover the United States up to 2/3 of a mile. If you were going to like go 1001, 1002, 1003, okay. So you're gonna like, all right, so our goal is to do that a mole of times, okay? Well, you could have, at the time this was written, the population of the earth was such that you could have 51,000 times as many people on earth doing that, okay, and it would continuously, nonstop, it would take us 75 years. Like, really?
To get to a mole?
To get to a mole.
Oh my God.
That's a big
That's
number.
a waste of time.
That is a waste of time. But we do a lot of things in science and math that I'm like,
There are people that
what's
would do that,
productive?
though.
There are people. So computers, computers are really fast, most of them, unless mine's on a Monday morning. But, so one of the things you could do with computers, maybe you know, is again, isn't very productive at all, but you can set them in this loop. And so if you've taken like programming courses, and you could have a computer go ahead and loop, okay? This computer can do 1,000 millions of instructions per second. In fact, this particular computer, if it were to do that, at the time this was written to count the US population, it would take 1 second, less than a second. But if you were to have that computer do a mole of iterations, it would take 1.9 million years, that computer. And again, what's the point? But still. Okay. Hockey pucks, a mole of hockey pucks would weigh the same as the moon. Basketballs, okay, the volume of a mole of basketballs would be equal to the size of the earth. Again, these are problematic. If you guys remember I Dream of Jeannie, where the genie owner would ask these crazy things, and some of them really went bad, and I can just see him asking for a mole of something, and it's not a good thing. So I think about the last one I have is this whole money thing. So if you're like me, you see a penny on the pavement, and what do?
Pick it up.
You'd pick it up? I don't.
I do if it's heads up.
If it's heads up, you do. Yeah, actually, I do kind of see what it is. But then if it's heads up, I'm like, well, somebody else might need it worse than I do, you know? I don't know. But if it's tails up, never.
I don't ever pick up money unless it's heads up.
So if you had a mole of pennies, and I'm almost, you know, when you handle pennies, you can smell that on here. So if you had a mole of pennies, that would be problematic. But it would be good and bad. You could actually, at the time this was written, divvy it up to the population of the world. And if you just move the decimal place over, okay, you see that's a lot of money. And at the time this was written, everybody would get 1.5 times 10 to the 14th pennies. Okay, and so if you move the decimal place over a couple places, that's 1.5 times 10 to the 12th dollars. All right, that's a lot of money. So we could all start spending at a rate of $1 million a day, and we would use up our wealth, or we use it up in about 4,000 years. So I wonder what that would be. But like they probably go to some other currency. I don't know. Probably deflate the value of money. Okay, but a mole is a bad thing because again, the whole land area, it's like the 1/4 of the earth. Would be covered up to 420 meters, which is bad. Okay, so enough with the kind of the silliness. So we talked before, and we're going to do this factor label method of working problems, but equivalency statements are our friends. They actually are ways to go to do conversion problems. So from any equivalency statement, and that's like Pee-wee Herman, you can go like this, okay, or you can go like this. Wait a minute, he goes like this, and then he goes like this. I don't know, something like that. But I'm just doing it like this and like this. Okay, these are what the inverse of each other. These are ratios we can plug in as conversion factors. And remember, we said as we work problems, we're trying to get our units to cancel and be left with the units we want to be left with. Okay. So we're going to go with atoms. 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. And I'm going to kind of do something here. Okay, 1 mole. Now, I'm not an English teacher, but 1 mole of atoms. That phrase right there is descriptive and great, and I'm going to go ahead and put it in brackets. Okay? Something in brackets at this point for me means it doesn't have to necessarily be there. So we could say 1 mole is equal to 6.022 times 10 to the 23rd atoms. 1 dozen is equal to 12 eggs. 1 dozen of eggs is equal to 12 eggs. Okay? Hope that's going to help us down the road. All right, so we're going to work a couple problems. Okay, now, and we're going to use those 2 ratios you saw. For one problem, we'll use 1 ratio. For another problem, we'll use another ratio, which just came from 1 mole is equal to 6.022 times 10 to the 23rd atoms. In the first case, and just to kind of remind you how we work factor label problems, I really encourage students to make this your first term and to make this your first term in the second one. The thing you want to convert. If you don't know how to start a problem, just take that and put it over 1 and include units, okay? So if we were going to diagram the first one, basically we are going to go from, we're going to go to how many moles, so question mark moles, again, of atoms is in brackets there, so it doesn't have to be there. Question mark moles is 1 trillion, and I went ahead and told you we're going with 4 sig figs. 1.000 times 10 to the 12th atoms. So we want atoms to cancel, be left with moles. So if you look at the previous slide, hopefully you can kind of see which one we're going to use for that. So that was 1. To diagram 2, it would look like this. How many atoms, so question mark atoms, is 0.555 moles. So that's it. Totally. So for the first one, like I said, we're going to put the 1 trillion hydrogen atoms over 1. So anybody want to throw out there which of the 2 ratios we're going to use? We want atoms to cancel, be left with moles. What do you think? Yep, we want to do the mole on top, exactly. So 1 mole over 6.022 times 10 to the 23rd atoms. So if you have your calculators, okay, you're going to want to be able to kind of maneuver scientific notation. So if you have your calculators, yeah, you're like me, it's hard to get away from these programming calculators. They're so nice. And I would like to say, if you can convince me that it's cleared and stuff, I might negotiate that whole. Because I love programmable calculators. So that I'm serious about that. So, okay. So it's 1, in my case, I put E12 divided by 6.022. Everybody's calculators are a little different, but that's mine, E23. Okay, so my calculator displayed something. Now, how many, since we're multiplying and dividing, we need to round according to significant figures. How many significant figures? 4. Okay, so rounding to 4 significant figures, is this what y'all got? 1.661, excuse me, times 10 to the minus 12. Yay. And then units would be, see, atoms cancel moles. You could just say mole or mole H, same thing. Great. Okay, so the next one, so like I said, now, in this case, we're going from moles to atoms. So the first term is gonna be that 0.555 mole, and I usually put it over 1 to emphasize I have units of moles in the numerator. Then what's the next term?
You put the atoms on top.
You put the atoms on top, exactly. So the next term would be 6.022 times 10 to the 23rd atoms over 1 mole. And then our moles cancel, we're left with atoms. Done deal. So I'll put that in my calculator. Okay, so how do we need to round this one? Is it 4 sig figs again? It's 3. It's just 3. Yep. So did y'all get this? 3.34 times 10 to the 23rd. So the first one was atoms to moles, and the other one was moles to atoms. So if you ever want to know what you can use something as a conversion factor for, you just look at the units. Remember, it's 20 after, not 16 after. Note to self. Well, don't worry, tomorrow we won't be counting a mole of anything, so you're in good shape. Okay, so these will both be due on, did you get that? Those next two problems will be due when we meet again Friday. Yes, fabulous Friday. So I got a few extra days, so I'm going to pull them up and see what we got. If you were here on time, you would hear the announcements. Okay. What are they, 6? What problems are they?
6.19, 620.
Thanks. All right. So 19, you have the answers to in the back of the book, so don't forget that. So your hint here is basically you're going from moles to atoms. So that's kind of like the second problem we did. So you're going to use Avogadro's number. And I pushed this out there under, as a PDF, I tweeted. So your first terms are going to be that number, and then you're going to use that equivalency statement as a ratio. So in fact, I even went ahead and did C for you. I set it up. So your first term is going to be the moles of mercury, 22.9 mole Hg, that's mercury. And then that second term came from the equivalency statement. We want moles to cancel, so we're going to put moles on the bottom, atoms on the top. That's it. The next one is kind of like the first problem we did, where we're going from atoms to moles. And your hint there is use those numbers as your first term. Every once in a while I have students that put the conversion factor like as their first term, and it works. You can swap those around. That's some property of math. So doing the first one, or excuse me, doing C, it looks like this. So you'll have to make sure we're all on the same page with regard to scientific notation. 7.91 times 10 to the 23rd potassium atoms, K atoms over 1. Then we want atoms to cancel, put moles on the top. And that's it. No need to make it harder than it is. Okay, so those will be due on Friday. So do you guys, you don't have this slide, do you? This is like a review slide. This actually was in the previous part where we're talking about the periodic table. And the periodic table, the box has two numbers. One number is the whole number. What's that whole number? Atomic number, very good. Whole number is atomic number, and that means what?
Number of protons.
Number of protons, exactly. And then most periodic tables go on and have what I call a decimal number. And that decimal number is how much it weighs in atomic mass units. Okay. So just a review slide, and this is another review slide we just talked about today. The concept of a mole. What does a mole mean? It means however you did it, you have 6.022 times 10 to the 23rd of those things. Rice grains, hockey pucks, pennies are problematic, but atoms are awesome. So for instance, if you were to have molecules-wise, if you have the compound water, it takes about 18 milliliters, which is maybe about this volume of my two fingers. If I have that much water, that's a mole of water molecules, to kind of put things in perspective. Okay, now on to the next thing, the next important thing in chemistry or physical science we need to talk about. The concept of a molar mass. I love the term. Not all terms are descriptive, but this really is. And I kind of go backwards. What is molar mass? It's the mass of 1 mole, okay? And usually molar masses are in grams per mole. Molar masses. Mass of 1 mole. Grams you have to set aside in order to just reach 1 mole, 6.022 times 10 to the 23rd of those particles. So remember I said when I work problems, I really avoid this G/MOL, that. So you have to unpack it. So actually unpacked, the units look more like this, grams per 1 mole. Okay. One more thing to kind of show you is this idea of now instead of showing moles in the denominator, you can show it's in the denominator by putting it with an exponent to a negative power. So the -1 means it's to the first power in the denominator. But this is my favorite. All right, molar mass. Molar mass is grams. You need to set aside in order to get 1 mole of those things. Well, that decimal number, okay, that I just said a minute ago is your average atomic weight in AMUs. That decimal number is the same number as the molar mass for the elements, for that element, excuse me. So we pick on carbon a lot. Do you guys remember what the decimal number for carbon is? Or you can look it up. 12.01. So a carbon atom, taking all the isotopic information into account, remember we talked about that Friday, is 12.01 AMUs for the element carbon. And for the element carbon, its molar mass is also 12.01, but 12.01 grams of carbon for 1 mole of carbon. That's how that works. Okay, it's the molar mass. Which if you think of 12.01 grams, that's not very much to get a whole mole of carbon atoms because they're just so small. They are just adorably small. Okay? Cool. So that decimal number serves double duty. So here we have sulfur and here we have carbon on watch glasses. And so somebody has gone and weighed out 12.01 grams. Why? Because now they know they have a mole of carbon atoms. The decimal number for sulfur, sulfur is atomic number 16. It's got 16 protons. The decimal number is 32.07. 32.07 grams per mole. So this right here for sulfur and this right here for carbon, it's kind of a physical property of that particular element. It's the molar mass. It's the grams per 1 mole of those atoms. okay? And so you're going to want to use it like that. Now, sometimes when you're using it in a problem, you might need to flip it so the units cancel that need to cancel. Okay. So these are just sulfur, magnesium, tin, silicon, and copper. And the point here is that somebody was clever and went and just weighed up the right amount of those substances to get 1 mole. So somebody tell me the symbol for tin. It doesn't, no, that's tungsten. It doesn't start with letter T. I think that's, it is SN, very good. It is SN. So what's the decimal number for tin?
118.710.
118.710?
Yeah.
Great. Okay, so for tin, and I usually say MM, if you see me write MM, that means molar mass. Molar mass of tin is 118.710 grams per 1 mole. That's it. Ding, ding, ding. Now, is there uncertainty in 118.710?
Yes.
Yes, there is uncertainty. How many sig figs are in that number? 6. That's a lot of sig figs. What we try to do is make that not the limiting term that makes us round according to that, and I think we're fine with that. All right. So you don't necessarily, oh, you guys don't have this slide. I'm going to kind of I'm picking on copper, and I'm going to do a proof to show you how we get molar mass for copper. So if you were to go to the periodic table for copper, you would see the decimal number is 63.55. And that's 63.55 AMUs. That's how much 1 atom weighs. All right? So, remember I said that the whole mass thing between grams and AMUs, I'm not likely to know how many grams 1 AMU is, but I'm more likely to know that 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. Okay, that is I want to say by definition, but it's not by definition. There's some uncertainty in those 4 sig figs. So AMUs cancel, and we're left with grams per atom. Well, if we introduce Avogadro's number again, now we are saying that we have 6.022 times 10 to the 23rd atoms in 1 mole. Kind of keeping up with terms that have canceled. This is like a little proof here, picking on copper. Our AMUs have canceled. Our atoms now have canceled. Okay, we're left with what? Grams per mole, which is the molar mass. So honestly, I can even do that math maybe. I don't even have to put 6.022 times 10 to the 23rd in my calculator because both of those terms cancel. So the number we're left with is 63.55 units are grams of, in this case, copper per 1 mole of copper. Yeah. You could do that for any element.
Yeah, so do you need us to show the work, or can we just do 63.5? Because technically it's just their weight.
Right.
You're just putting their atomic weight over 1 gram.
Right. I think to answer your question is you'll never have a problem kind of like this.
Yeah.
But this is just to show you that that decimal number actually counts for how much it weighs, 1 atom weighs, and also is the molar mass. Yep. Very good. All right, so let's do some molar mass calculations, shall we? Let's pick on calcium. So we're going to need the periodic table. Do you guys have a periodic table for your tests? You don't have to memorize these things. We have black and white periodic table. That one we won't be in this room. But if we are in a room that has a periodic table with the names, then I have to blacken it out. So this one, we are going to, and it's nice to kind of dissect a problem sometimes. So how many moles, so on the end, I put question mark moles, okay, is 0.487 grams of calcium. 0.487, I could put grams or grams of calcium. Oops. So I want to go from units of grams to moles. So if you look up calcium, you'll see the decimal number is 40.08. 40.08 grams per mole. 40.08 AMUs per atom. Okay? So I really would encourage you to unpack it 40.08 grams per mole, just for calcium. 1 mole will weigh 40.08 grams. Sometimes I kind of like this flattened out one. It's a physical property of the element calcium. 1 mole is equal to 40.08 grams, just for calcium. So this time, let's try this. I'm going to call this first ratio A. I'm going to call the second ratio B. And let's just see which one of these two that we're going to want to use. I see some people already working it. Okay, here we go. So, what's the first term going to be? What do you think? It's not going to be either one of those ratios, A or B. What's the first term going to be? 0.487. 0.487 grams. I usually put it over 1. I'm going to ask you A or B. Okay, so we want grams to cancel. We want to be left with moles. How many people think we'll use A? How many people think we'll use B? The B's have it. So if we use B, then actually 1 mole of calcium over 40.08 grams of calcium. Remember, we got that from the periodic table. Now our grams of calcium cancel, we're left with moles of calcium. And that's perfect. So how do we need to round this?
3 sig figs.
3 sig figs. I'm liking it. So to give it 3 sig figs, this is one of those where we have a leading decimal, or excuse me, leading 0 after the decimal. So this first 0 is needed because it's a placeholder, but our sig figs start with the non-zero digits. Any questions about that? Cool. I'm liking it. Okay, let's do one more. We're going to pick on boron. Okay, so again, if we were going to diagram this, what mass in grams? So I put question mark grams is 1.33 moles of boron. 1.33 moles. So I want to go from units of moles to grams. So this is where we pick on boron, and I'll kind of show a similar slide as I did before. The decimal number for boron is 10.81. And the decimal number means 2 things. It means how much in AMUs on average, weighted average, boron atom weighs, and it also is the molar mass. So 10.81 grams per mole. We're going to make that A, and we're going to make the inverse B. 1 mole boron over 10.81 grams boron. All right, so let's work this problem. What's our first term going to be?
Our first number?
Yep.
1.
Thank you. 1.33 moles boron. And in both of these problems, the first one calcium, this one boron, since we're only dealing with one element, we don't really have to be explicit with the element. You could just put 1.33 moles over 1. So I'm going to ask A or B. How many people think we should use the A ratio? I think so too. The reason we use the A ratio is now our moles of boron will cancel. So the next term is 10.81 grams, or grams boron, over 1 mole, or 1 mole boron. So the moles of boron cancel, we're left with grams, and that's exactly where we want to be. So how do we need to round this one? 3 sig figs again. You almost look like a rapper. Okay, so I got 14.4 grams. We good with that? Okay. So what I'd like to do is kind of look ahead. I'm skipping the next, I think there's 2 problems. Go to the assignment slide if you would, please. And I want you to do 20, and we're going to take a look at them right quick. I want you to do 29 and 30 for Friday. So let's just take a look at that one. 29 and 30 will also be due Friday. And then we are going to do those problems we'll start with those on Friday. I think that would be a good way to go. So here's 29 and 30. Again, remember 29, the answers are in the back of your book. So how many moles of atoms are in each elemental sample? This is like one of the problems we just recently did. So we're after moles in each case, and we're given grams in each case. But we're going to have a different molar mass for each element, aren't we? So I picked on C to kind of show you setting it up. What's TA stand for? Is that? Anybody know? Is it? Inquiring minds.
73.
Oh, yep. Thank you. Tantalum. Tantalum. There you go. The element tantalum, the molar mass is 180.95 grams per mole. So just to kind of remember how that goes, your first term is going to be the mass you want to convert, 72.5 grams, TA, over 1. And the second term is going to be from what you got off the periodic table, grams per mole. You want grams to cancel, and you want to be left with moles. So that's what I call the flipped version of the molar mass. And that'll get you there. And then for the next one, what does W stand for? Tungsten. Yep. Very good. So for the next one, we are, what is the mass given these moles? Again, were you going to use the periodic table and pick off the molar mass for all those things? Okay, and I picked on C, the molar mass of xenon from the decimal numbers, 131.29 grams per mole. So we're going to use that as a conversion factor. Our first term is going to be the 68.1 grams of xenon, 68.1 moles of xenon over 1. We want moles to cancel, so we use what? The unflipped version of the molar mass. That's it. Okay, so do those 2. Wait, yeah, do those 2 in addition to the other one. Any questions? Great. Well, get the word out. No class on Wednesday, but lab on Thursday.